Hello and welcome to a set of videos introducing the basic concepts of plate tectonics. I've designed these presentations to be appropriate for three levels of learners. Number one is the person who's never had any background whatsoever in plate tectonics. Here's the place to learn the basic concepts and ideas. Secondly, there could be the student who has had an introduction to plate tectonics before but needs a little bit of a reminder and review. Thirdly, there are those of you who might view yourself as experts in plate tectonics. You've studied it before, you've been tested on it before. Here, I'd like you to look at these videos and think about what it is that I'm not telling you, what I've left out, where the controversies continue beyond what I have to say. So these videos are organized into four different presentations. The first one is Plate Tectonics, an observational fact. These will be followed by a discussion of Earth layers and topography, boundaries and processes, and finally earthquakes, magnetics, and hot spots. Let's begin. Okay, learning goals for this first video. I want you to know something about the geography of plates and their boundaries. You need to know that Earth transports its deep heat by a process known as convection. And thirdly, you should understand some of the basic ideas of history in the 20th century of plate tectonics. So on the first topic, geography of plates, you'll need to know after this video that there are about 12 major plates, and you need to know the general directions and rates that these plates move. You need to know the four kinds of plate boundaries, and that about 200 million years ago, the continents were arranged together in a supercontinent. On the Earth transport of heat, plate tectonics is simply the surface manifestation of a deeper level convection within the mantle. On the history of plate tectonics, you need to understand the rise from continental drift to plate tectonics all over the course of the 20th century. So let's push that aside and move on to plate tectonics, which is simply an observable fact. It's not the theory of plate tectonics. Well, we certainly can talk about theoretical aspects of plate tectonics, but plate tectonics itself is an observable fact. First of all, large plate-like areas, big rigid blocks on Earth's surface move coherently. Those are the plates in plate tectonics. We know this because we have GPS measurements with nowadays millimeter accuracy taken over several years. So if you know where you are year by year to millimeters, you can determine that the plates are moving and that these movements confirm geologic and geophysical evidence collected over the last 100 years that continents have moved very large distances laterally over the course of geologic time. The rates of these plate motions are variable from 10 millimeters a year to 120 millimeters a year. So how big is 10 millimeters? Well, that's half an inch-ish, so it's, the width of your finger. 120 millimeters, well, that's something like about 6 inches. So imagine areas on the Earth's surface shifting over 6 inches at a time year by year. Well, 6 inches a year turns out to be about 120 kilometers in a million years. And there are lots of millions of years in Earth history, so plates can transport blocks of land by very large distances across the Earth's surface. So let's talk about what these plates are. There are about a dozen large plates. The largest of the large are the American plates, actually a North American plate and a South American plate. There's the African plate, the Pacific plate, very large plate, the Eurasian plate, another large plate, the Australian Indian plate, and finally the Antarctic plate. You should know those major plates. In fact, they're named by the continents lying on the plates. The only plate without a large continent is the Pacific plate. Here's a map showing plates and boundaries and directions of motion. Now, if the Earth's surface is all in motion, it's a bit hard to tell what the coordinate system is, motion relative to what. But for now, let's take Africa as being stationary. So if Africa is moving 0 millimeters per year, let's ask how the other plates are moving relative to Africa. Well, to the north of Africa lies the Eurasian plate. It's moving about 7 millimeters a year, and actually it's moving south towards Africa at about 7 millimeters a year. So there's a convergence of those two plates along a trend that includes some of the active tectonic regions in the Alps and the Mediterranean. Now over here is the North American plate. It's moving away from Africa at about 26 millimeters a year. South America is moving away from Africa at about 32 millimeters a year. Antarctica also moving away from Africa to the south at about 9 millimeters a year. Finally, there's the Indo-Australian plate also moving away from Africa at about 54 millimeters a year. Notice, plates generally moving away from Africa, only Eurasia moving at a very slow rate towards Africa. Now, if we move to the Nazca plate, the small plate adjacent to South America, and you see Nazca plate is moving towards Africa at about 50 millimeters per year, or 50 kilometers per million years. Now, with Nazca plate moving towards Africa and South America moving away from Africa, we have a boundary between those two of convergence at about 82 millimeters per year. Then there's the Pacific plate, and if I move over this way, here's the Pacific plate. The Pacific plate is moving away from Africa at about 100 millimeters per year. So now let's talk about the 4 plate boundary types. And why are there 4 plate boundary types? Well, there are only 3 things that can happen to rigid plates on a sphere with constant area. The plates can either move towards each other, convergence, they can move away from each other, divergence, or they can move side by side. So there's 3 basic directions of motion. The first, divergent motion, we call these spreading centers. Spreading meaning spreading apart. Magma rises to form new oceanic crust in the spreading centers, and 2 new plates are born along the spreading center. Now, convergence can occur in which one of the plates subducts. Usually it's an oceanic plate, and I'll talk about more about that in a moment. A convergent margin with a subduction zone has one plate going down and one plate overriding. A convergent zone with 2 continental segments can't subduct in the same way. In fact, the continents tend to plow into each other and push up, forming a mountain range. So convergent margin with continents generates high mountains. Finally, side-by-side motion, the transform motion, 2 plates simply sliding adjacent to each other with neither convergence nor divergence at the boundary. So let's look at the world in this spherical representation projected onto a piece of paper. We have the Pacific plate in the Western Hemisphere, and you notice Pacific plate's very large. It has no continental areas on it. The Pacific plate has along its southeast margin an extensive spreading ridge center. So there's spreading center extending all the way around from the Americas to Australia along the shores of Antarctica. The Pacific plate is moving towards the northwest and eventually subducting in a convergent zone which extends from Alaska all the way across into Asia and Southeast Asia. In a middle section here, principally in California, you can see that the 2 plates are neither converging nor diverging. This is a transform motion. North America and the Pacific plate have relative motion of side-by-side motion. Just to the north of that, in the Pacific Northwest, you'll notice that there's some very complicated arrangements of spreading, transform motion, and convergence, and I'll talk about that a little bit more in a moment. So now let's go on to another view of plates on an Earth and focus in on the spreading center in the southeast Pacific. This is the East Pacific Rise. I've circled an area there. Let's blow that up and look at what the seafloor looks like. Here's an image produced by sound waves. It's a sonar image of the seafloor, and you notice that there are very regular features about center points. And so these two yellow lines here are identifying where spreading is occurring. So along those lines, there's a divergence of the plates moving away from the spreading center in the directions indicated by the arrows. Now, you notice that these spreading centers are offset. There's a zone in between in which the motion of the two plates is side by side. There's a transform fault separating two spreading centers. Now let's focus somewhere else. Let's look at the Pacific Northwest. I told you it was complicated. Well, let's look at how complicated it is. First of all, to the south in California, we have the side-by-side motion in the San Andreas Fault, the transform motion of no convergence or divergence. To the north of that, we have the Juan de Fuca spreading center just off the coast of Oregon and Washington, the white arrows indicating the divergence of the plates along the Juan de Fuca spreading center. Now, as that Juan de Fuca plate impinges on North America, it subducts along a trend indicated by the green line, which is labeled here the Cascadia subduction zone. We'll talk about it more, and then to the north of that is, again, a transform boundary, the Queen Charlotte Fault. So now I've drawn in here a trend of volcanoes. This is called the volcanic arc, and a consistent feature of all subduction zones is a volcanic arc, and we'll talk more about this as this progresses. Let's look at subduction where it's not an ocean impinging on a continent, but an ocean impinging on an ocean. And here in the area of Guam, we have the Pacific Plate to the east and the Philippine Plate to the west. The Pacific Plate is impinging on the Philippine Plate, and it is, you can see it's pushing in against the Philippine Plate, and it subducts along a trend indicated by the arc there. Just behind that arc is an arc of volcanic islands. Naturally enough, we call that the volcanic arc. Let's move around to the other hemisphere. Here we're looking at an African-centric view of the world. And let's focus in on this area in East Africa. This is an area that has tried and maybe is trying to split apart to form a new plate boundary. And if we zoom in on that area, we see scenery like this. This is the Great East African Rift. On the other hand, if we come across to the area highlighted here over in northern India into Tibet, we have a collision area between the Indo-Australian plate and the Eurasian plate. The idea is simple. India was a subcontinent separated from Eurasia prior to about 50 million years ago. India was moving northward. You can see this northward movement. Well, it's moving that way in this photograph, or in this image. And about 50 million years ago, it collided with Eurasia. In the collision area, we formed a mountain belt in a highly elevated region, and subduction stopped in that area, but continued pushing of the continental masses together has led to an elevation of the whole region, forming the Tibetan Plateau and the Himalayan mountains, highest mountains in the world. Let's talk a bit about past location of the continents. Here's a reconstruction from 200 million years ago. You can see highlighted in yellow at the bottom. And 200 million years ago, you can see that South America, right up against Africa, Antarctica, India, Madagascar, all tucked in along the east shores of Antarctica, not east shores of Africa. and North America pushed in against the bulging northern part of Africa. Now what happened? Well, that was 200 million years ago. If we step forward, a few other notes. This southern arrangement of continents we call Gondwana land. Now, the arrow pointing north is to Eurasia plus North America. That is lumped together and described as Laurasia. The combination of Gondwana land and Laurasia into a single supercontinent is called Pangaea. We move forward in time now, highlighted in yellow at the bottom, to 120 million years ago. And what's happened between 200 million years and 120 million years? Well, in the North Atlantic, about 180 million years ago, North America split off from Africa and it started heading towards the west. Along the boundary between South America and Africa at 120 million years, they are just splitting apart. And you see a separation opening up, a rifting occurring, much like the East African rift today. There was the rift between South America and Africa that opened up enough and formed a new ocean. Notice that India, way over there, has separated from its position tucked against Africa and is moving towards the north for its eventual collision with Asia about 50 million years ago. Okay, mantle convection is inevitable for Earth. There's a statement for you. Let's talk about what convection is. Simply stated, if you heat the bottom of a viscous material, it can thermally expand at the bottom. When it thermally expands, it becomes lower in density. When it's lower in density, it can become buoyant compared to the fluid around it. As it becomes buoyant, it can rise to the top. Having risen to the top, it delivers its heat to the surface, at which point it can cool down. As it cools down, it contracts. As it contracts, it gets denser. A denser material then will sink. So we have a cycle here, from sinking to rising to sinking again. This sinking rising cycle, delivering heat from the bottom to the top, is convection. Convection is a phenomena we see all around us all the time, from the soup boiling on the stove to the atmosphere on a warm day as thunderstorms develop. The tendency to convect in any system is characterized by a number called the Rayleigh number. What's the Rayleigh number? It's a big word, but it's a simple idea. If you make a ratio of buoyancy forces to viscous forces, buoyancy forces wanting to cause the material to rise or to sink, the viscous forces impeding the tendency to rise or sink. Obviously, if buoyancy forces are large compared to viscous forces, a system can convect. It can rise up and sink down. However, if the material is too viscous, very large viscous force, then it can impede the convection. From theoretical studies and laboratory studies, we know that systems tend to convect if the Rayleigh number is greater than 1, and typically a number of about 1,000 is appropriate. So as long as buoyancy forces are 1,000 times or more larger than viscous forces, a system convects. So mantle convection is inevitable on Earth. Earth has internal heat. What is the internal heat? It was the primordial heat, the heat that it obtained when it originally formed, and it has radiogenic heat, the heat produced by the decay of radioactive elements trapped within the solid Earth. That heat is always being transported. It's going from where it's hot to where it's cold. Near the surface, that heat is transported by a process of conduction. The same way heat gets from the stovetop into the boiling soup pot through the solid pan. Now, once you get into a convecting system, the heat is being transported by convection, and convection is the process within the Earth, within the deep mantle. So, For convection to occur, the Rayleigh number has to be greater than something like 1,000. The Rayleigh number for the Earth's mantle is not accurately constrained. However, it's likely large. No matter how you cut it, the Rayleigh number has to be somewhere between 1,000,000 and 1,000,000,000. Now, 1,000,000 and 1,000,000,000 are both very large numbers compared to 1,000. So even though we're uncertain about the Rayleigh number, we know it's very large. And because it's large, the mantle is convecting. Another way of putting this, though, is that in Earth, only convection can remove heat fast enough to keep the interior from completely melting. If we didn't have convection, the Earth's interior would lose heat too slowly. The radiogenic heat produced within would cause it to get hotter and hotter and hotter, and eventually, if there were not convection, it would get hot enough to melt. Convection is in fact keeping the mantle cold enough so that it is always solid, but it is hot enough to be ductile enough to convect. We'll talk about this more in the next video. Earth's surface is in motion. It's in motion laterally between regions of the mantle that are upwelling and regions of the mantle that are downwelling. This lateral motion of the surface is what we call plate tectonics. So, simple model, boiling soup pan, heat at the bottom, rise to the top, flow to the edges, sink to the bottom. Turn the cartoon for the Earth, and we have a pattern of convection, of deep heat rising, and cold rock sinking. Now, how did we come to understand that plate tectonics was the process by which the Earth worked? I'm going to title these slides From Hypothesis to Fact, and it's a brief 20th century history of plate tectonics. Well, even before the 20th century, back as far as when the first maps, accurate maps were made, the jigsaw puzzle-like features of Africa relative to South America were noted, and it was conjectured that there might have been some connection between Africa and South America. Early 19th century to mid-19th century, a lot of robust geologic observations were made that suggested continents had a different arrangement in the geologic past. Some of these lines of evidence included similar fossils of extinct animals on separate continents in past eras, whereas those continents have different assemblages of animals today. So if the continents were together, it made sense that they were similar. If they're apart, evolution could lead to differences. Another line of evidence is glacial deposits found in equatorial regions and coal found in Antarctica. Now, climates can change, but getting it cold enough to have glaciers at the equator and coal at the poles at around the same time seems a bit strange. Finally, geologic strata line up when you put the continents back like a jigsaw puzzle. So it's not only that the coastlines of Africa and South America align so well, but that by aligning it, the pattern on the jigsaw puzzle also matched. The geologic rocks in South America matched in age and character with the geologic rocks in Africa. Well, let's look at the early 20th century, and an early pioneer in forming a solid hypothesis that could be scientifically tested was Alfred Wegener. Alfred Wegener was an Austrian who served as a meteorologist and polar explorer doing early scientific investigations in Greenland. He developed a comprehensive hypothesis for continental drift. His book, first published in 1912, was titled Origin of the Continents and Ocean. The book was widely read, widely considered, and not completely rejected by the mainstream scientific community. At that time, they pointed to his mechanisms of motion, which seemed inadequate. The causal mechanism for his continents to move just seemed wholly inadequate. Scientists of the time felt that there were alternative explanations for the observations. I mean, really, what are more mobile, animals or continents? And if there are differences or similarities of animals, could that just simply imply migration paths rather than moving continents? Well, moving forward in time, the plate tectonic hypothesis was born around 1960, and it came in with an idea that thermal convection was possible. And if thermal convection occurs within the mantle, you have upwelling here, downwelling here, there has to be a connection of horizontal motion at the surface. At the same time, new geophysical data were obtained that supported this basic idea, and these geophysical data were principally magnetic, seismic, and they explained the older observations and circumvented the earlier objections. In the mid-1960s, the paradigm shifted. Continents had to move, not that how could we make continents move, which was the great argument in the 1920s. So that brings an end. My first video, Plate Tectonics, is an observational fact. Coming up, I'll talk about Earth's compositional and mechanical layering.